As you guys know, MongoDB is coming out with multi-document ACID transactions in 4.0. And we put this little video series to walk through some projects on how we got here. One of those projects is creating safe secondary reads. I'm Allie Cabral, a product manager on the core server, and I have Diana with me, an engineer on the core server, and she's going to walk through this project.
Thank you, Allie. So let's define some basic concepts about what a replica set is and a shard before we go into project specifics, because we need to know what they are. All right. So a replica set consists of a primary and some number of replica sets. The primary can accept reads and writes, and the secondaries basically just they replicate the data. They don't do anything else. If they're there for if something bad happens to the primary, like it crashes, we can elect one of the secondaries with all the same data and have a new primary and keep going. So the concept of a shard comes in a cluster. When we have a cluster of replica sets, we tend to talk about the replica sets as a shard.
And each shard owns a piece or partition of the data.
Yes. So you have a collection of data, and we take a little piece of it and we stick it on a replica set, and we call that a shard because it has a shard of the data. So here is a shard. So along with the concept of a shard, and now we have pieces of data all over the place, we need to know where it is. So we have this concept of a routing table, which says this replica set or shard owns this piece of data. So if a query comes in, it can look at the routing table, or we look at the routing table, and we direct it to the correct shard, or it might be several shards. So where this project comes in, the primaries before this project knew about the routing table. They could service requests and say, like, I have that chunk, I don't have that chunk, go somewhere else. Secondaries don't have this concept, so they are unsafe when we do data migrations.
And when you say chunk, a chunk is a piece of the data, like a small piece of the data.
Correct.
Mm-hmm.
So we take a piece of a collection of data and we split it into chunks conceptually, and we move a chunk to a server, so like a little range of the data. So yeah, secondaries they don't have the routing table, so they service whatever requests, and this is a problem for migrations, which move data around and can create temporary two duplicates of the data. So let's go look at a migration and show you how that can be a problem. All right. So there are 3 steps to a migration. The first one, so we have starting off with a chunk on shard A. And so the first step is to copy the chunk to shard B. So we'll copy it over here. The second part of a migration, we will go and update the routing table. So we cross that out. And now chunk lives on shard B. And then the third step, we go and delete the original data. So we cross this out. The problem arises between step 2 and 3. Because we can't do this all like magically at once. It's a distributed cluster and different servers. You can't do it at once. No atomic idea there.
So between 2 and 3, the data exists on both of the nodes.
Yes. So what do we do? Let's start with what can happen if in this situation. So let's go back to this data's not quite deleted yet. We have the routing table, that's updated, but this chunk isn't. All right. So if a write comes in, say to the system after we did the copy, it properly does a write on the new shard. And now that chunk has another document, or it updated a document. And suppose it was like a majority committed, so the user really wants to make sure that data is there. A query comes in, it has stale information about where the data is. You have a query, and you don't see that write that happened over here. So you're like, where did my data go? Another thing that can happen is if you do a range query that goes to multiple shards, and we have 2 copies of the data, you can get 2 documents back. And it's like you queried for 1, suppose you had a unique identifier in that document and you got back 2. And you're kind of like, huh?
That's unexpected. So how does this work on primaries?
Yes. So primaries have a routing table. They know what chunks they own. So once we copy the data and we update the routing table, we have a process for making sure everyone knows about that before we allow any more reads. We update the routing table, the ownership is switched. This query won't work anymore. It'll be rejected, and the caller will be told to go talk to shard B. And then the scenario would work. You do a write, you do a read, you see your write. And you can't service, if you do a range query, you can't get duplicate documents. All right, so that works on a primary, but secondaries don't have this, so they are liable to all the problems we talked about. So why do we want to do this project? Let's take a moment for that. There are 2 reasons. For transactions, what we really wanted was we want to be able to extend the features in that roadmap to secondaries. So we don't want to just involve the primaries. Like, we have transactions on primaries, but you can't do anything with secondaries, otherwise nothing works. That would be sad, because we have cool features and we want it to work everywhere. The other thing is the project by itself is, I think, pretty awesome because it lets some applications can't query secondaries before we did this because they needed to see consistent data. They couldn't deal with duplicates or not seeing your own writes. That's not something they can handle. So now that we've extended the primary's capabilities to the secondary, they can gain an order of magnitude of availability. So you have 4 replicas in a replica set, and now you can query 5 servers safely.
Great.
So that load is distributed. So how did we fix this? Let's go down here. So before the project, we only ever had on shard primaries, we would have an in-memory cache of the routing table. The shard would know I own these chunks, and that was pretty much it. Secondaries, since they're not the primaries, they had nothing. They didn't have any in-memory state. They weren't chunk aware, so to speak. And you could happily, like, suppose a data migrated. So let's see, we have chunk 5 on the primary and secondary. Oops, a little bit small. And in the cache of the routing table, we know chunk 5 doesn't belong on the shard primary. So if a query comes in, we'll filter out chunk 5 data points. On the secondary, however, the query would work. We'd see chunk 5, and that'd be bad because some other server has it, and who knows?
So secondaries return all data on the node regardless of ownership at all, because it wasn't aware. And this is pre-3.6, that is.
Yes. All right, so how did we fix this? So what we did in 3.6 is we persisted the routing table cache on a shard primary. So now it has this cute little table here that tells it all the shards, who owns what chunk, and it can, same as before, the shard primary can still filter out results. So again, it has like chunk 5 hanging out there, but chunk 5 right here, you can see it, is on shard B somewhere else. So it won't return those results to the user. And so persisting it allowed replication to take it away down to the secondary, which now has the routing table and can load it up into memory and again provide the same services as the primary. So now if a client queried the primary or the secondary, it would safely not see this little red chunk that's been moved off somewhere else. He's pending for deletion. He hasn't been deleted yet. It will be soon. And you don't see any of the bad results. So that's how we fixed it. The externally visible part anyway. It's more complicated than that. And so let's finish off with an example of one of those nice transaction features that we can now do on secondaries. So I'm going to bring in causal consistency here. I'm not going to talk about the overall project. Someone else is going to talk about that. But one of the things that causal consistency introduced was the concept of an after cluster time. That's what this is, after cluster time read concern. So the idea was now when servers talk to each other, we have this cluster time that we communicate, and we pass it around and always up it. So you can say, I want to read on this server after this cluster time. So how is this helpful? So what happens in this example, so we start with number one, the client does a write to the primary. So it says, I'm going to update _ID 5 and have it have page 4. So it's doing some write. That write will generate a cluster time, which will be returned in step 2 to the client. And now the client has the time of that write. So it can go to the secondary. So it can do number 3, read after cluster time of that write to the secondary, and ensure that it'll wait for replication before it'll give you the response. So this will now have page 4, sorry.
So the read will not be returned until that secondary has caught up to the time of the write.
Correct.
Right.
So you know that the data is there. So I did a write. The client did a write on the primary at this time. I'm going to go to the secondary and wait for that time to be there as well, and the data with it before returning for the query.
So regardless of which node you're speaking to, you're always seeing forward in time.
Yes. You never see backwards in time like before replication happened.
Right.
And this is cool because you can read your own write. So you do a write to the primary, and now you can read it on secondary, and you couldn't do that before. So that's why it's cool.
Awesome. Well, thank you, Diana, for walking through this project.
Okay.
Awesome.